Russians are the overachievers.
Okay. Is it because the video is really helpful, or is it just because my stare is really intimidating? Except for the three bold people who can take it.
Everyone's getting empathy.
Okay. Or is it just that you're not going to sit right in front of me unless you have to? Except you're all sitting where you always sit. So it has to be that just these people dropped out.
Maybe they thought you had a cold. Knew you had a cold today, and they were like, let's stay out of the line of fire.
They knew it. I was going to sneeze all over them. Okay, so I have your midterms. I'll pass them back at the end. When we get close to the end, please remind me to shut up and pass back your midterms. Otherwise, I'll forget. And okay.
I forgot to charge the battery for this thing, so.
Okay. Well, I will record on mine. And it's recording. Okay. Let's start by visiting our schedule and getting the high-level overview, like we always do. AI, schedule. Today is April 7th. This is today. This evening at 7 p.m., John Conway's speaking. That would be cool to go to. I wish I could. I hope somebody does, because I want to know what he says. I want to know why microscopic particles have free will.
You know, you can actually find his paper online for free.
Ah, okay.
I was reading it before class.
Cool. Is it like a proof by contradiction that free will is nonsense, or is it, or does he actually believe little particles make decisions, or what's the?
He's not using free will necessarily as in the way it's colloquially used.
Oh, okay. So it's some other definition of free will.
It's similar, but not quite the same.
Interesting. Well, let's have a big discussion about it next
You can also get a
Tuesday.
high-level overview on Wikipedia.
Okay. Well, cool. Sounds interesting. Anyway, that's the thing. So, I pushed assignment 6 back till. Where'd it go? Assignment 6 is due a week from today, and I wanted to go over doing assignment 6 today, so you'll have a full week to do it and the weekend. But most of you will end up coding it up over the weekend, I assume. Isn't that usually when you do projects? No. Half of you will do it Wednesday night, starting at midnight.
Thursday night.
Thursday night, starting at midnight. Okay. The slackers will start Thursday morning. Okay, well, let's make sure it's very clear what you're doing. So, you're going to implement a random forest class.
Virus.
I didn't tell you how to report the results. I need to update these instructions to tell you how to report the results. Okay, well, I think the best way to show you is to just, let's do it. Okay, how about RF2? Okay, how about RF3? There we go. Save. And let's go do it. RF3. Supervise. Okay, so last time we left, I think I was showing you the data, and we showed you that there's some interesting data here. Remember that? For example, the vowel train features contains Mel frequency cepstral coefficients for audio that somebody recorded saying a bunch of vowel sounds. And by somebody, I mean Mike, Andrew, Joe, Nick, Penny, Wendy, Sarah, Rose, and so on and so forth. And we're going to train a decision tree, or a random forest, an ensemble of decision trees to basically figure out what vowel they were saying. Okay? So this is called supervised learning. Supervised learning kind of has two phases. First, there's a training phase. And in the training phase, you make a model, and the model can be used to make predictions. And then there's a testing phase, and in the testing phase, you're seeing how good your model is. Or maybe you're using it to actually do something. Any questions about that? Do you get supervised learning as a concept? Do I need to clarify anything? That's kind of it. Okay, so when I say training, I'm talking about the process of producing a model. What's a model? So model is kind of like a function approximator. Do you remember when we were talking about neural networks? I said, suppose you have some data points that look like this. And I said, here's one possible model. And here's another possible model. That's a pretty good model, right? Maybe. And then here's another possible model. How good is this model?
3 out of 10.
So it's kind of a trick question. I'm asking you how good the model is, and well, as far as predicting the training data, it's just about perfect, right? Because there you go, the model perfectly predicts the training data, therefore it's a perfect model, right? Well, except for this point right here, I missed a little bit. That's due to the sloppiness of my mouse. But is it a good model? Well, what determines whether a model is good is how well it does on data it's never seen before. Doesn't that make sense? If the model is useful, if you feed in some point you've never seen before, like I say, hey, what happens if I have a value that's right here? What's the y value? And if the y value is exactly right, I missed. If it's exactly right there, that's one data point saying good model, right? And if I feed in, say, this value for x, and it turns out the true y value for it is right there, that's a data point saying bad model. Now it's getting confusing. Do you see that it's possible that this could be a really, really, really good model? It's possible if all of the points we've never seen before, which I'll draw in green, happen to be right along where it predicts. If that is the case, this is a fantastic model. However, it's quite possible that the data points actually look like this, right? This is also plausible data, and if that's the case, then wouldn't this model have been better? I mean, which model is better, the complex one or the simple one? Yeah, so in general, simple is better than complex. What principle do we call that? That's Occam's razor. Now, Occam didn't actually work with machine learning models. I don't know what he did. I think he was a Catholic monk. I don't know what he worked with, but he was the first guy to really say, hey, don't complicate things more than is necessary. And he's attributed with the whole concept. So the concept is this: you really want a model to be as simple as possible to explain the data. But what's interesting is actually, Occam's razor doesn't say this model is better. I kind of said it did, and it doesn't. Occam's razor, yeah, liar. Okay, Occam's razor says that this model, again, we're going to say black is the training points, and green don't yet exist as far as we know. Can you even tell the green on this screen? No. Okay. There could very well be another model. Goes like this, right? It does. The sound effect is really important. I have a brother who's an artist, and he makes sounds while he's drawing, and it's so amusing because everything is and I guess we have the same genes. Occam's razor does say this is a bad model. Why? Because it's more complex than there is any data to justify. And maybe you do have some reason for being complex, but if that's the case, you have more data, right? You have some reason to make it complex, or else you don't. And Occam's razor says, unless you have a reason, don't make it more complex than is necessary. So, more complex than this one is pretty much bad. But what about simpler than this one? Is simpler than this one better or worse?
I think this is more data points.
Well, yeah, it actually depends on the training data. Now, since we see, it depends on the test data. Since we can see this test data, we can see the simple model is just as close to the test points as the complex model. Therefore, given that extra information, now we know the simple model's better. But if we didn't see the test points, we would have no basis for knowing the simple model's better, and Occam's razor would say nothing about it, because, in fact, this simple model misses the training points, right? But it hits, well, it comes close to the training points, but it doesn't hit them, whereas the complex model hits them all precisely. So here's the grand question: how do you know whether you should fit your data totally, or whether you should just fit your data pretty close and keep your model simple?
Be aware of margins of error.
Maybe. What does that mean exactly?
Not exactly sure.
Okay. Well, I'm going to claim that if all you know is the training data, if you don't have test data, there's no way to answer the question. Because it's very possible the test data looks like this, but it's also possible the test data falls right on the point. And because the test data is what defines the answer, it's not known whether the simple model or the more complex model is better. Does that make sense? Okay. So how do you actually determine? There's another technique, which I think is slightly more powerful than Occam's razor, called cross-validation. I'll write that up here. Cross-validation, just because that's an important concept. Cross-validation, the idea is you take your training data and you break it into two parts. So shuffle your data, put half of it over here, half of it over there. You train on half of it, and then you test on the other half. You see why that's a useful thing to do? What it does is it tells you how good your model is. If you had a bunch of candidate models, you could find out, oh look, this one makes good predictions, and this one makes bad predictions, and the one that makes good predictions is better. And cross-validation kind of answers the question. So when you ask the question, how simple should your model be? Occam's razor says no more complex than you have data to support. But in reality, that's not strong enough. Your model should be even simpler still. And cross-validation answers the question of how simple should it be? Well, whatever level of simplicity maximizes predictive accuracy, maximizes your correct predictions of the test data, that's the right amount of simplicity. So cross-validation is a very important concept in supervised learning. It answers the question of how do you know how good your model is? Did you follow that? Okay. Now, we've been drawing curves here with neural networks because it's like a function, right? Neural networks have values that go in and values that come out. Assignment 6 is the next one, right? Is about decision trees. Are decision trees functions? Remember, we've been drawing pictures like this, where we have red points over here and blue points over here, and then we divide them with lines and say blue's over there and red's over here. And we'll say, okay, this whole region is blue and blue, and then you have pink. That didn't come out the color I thought it would. Anyway, you get the point, right? This is kind of a decision tree. How is that a function? Or is it a function? Or is this thing even the same thing as this thing?
like a Boolean function, like it's one or the other?
Yeah, so it's, in that case, I was using red and green. I could draw it another way. Red's up here. Well, I guess this is red and this is, I use blue or green? I use blue. And then for different values of x, it might look like this. Do you see that this is kind of the same thing as this?
I'm not sure what you were trying to show us.
Okay, well, in this case, I have one input dimension, which is the horizontal axis, and one output dimension, which is the vertical axis. And on the vertical axis, I have two possible values, high or low, which I've labeled with red and blue. And so I'm saying that if various regions of your input space are mapped to binary outputs, that's sort of a function, right? Well, if we draw it this way, now we've got two-dimensional input space, horizontal axis and vertical axis, and now I'm using color to represent the output. So this is a two inputs, one output function, and the two inputs are continuous and the one output is binary. You see that? So these are just, really these are kind of different ways of drawing similar concepts. I mean, not the same, because this is two dimensions of input and this is one dimension of input. Now here, when I draw a function like this, I'm trying to suggest that there's one input dimension and one output dimension, and they're both continuous. Do you see that? In this case, I use color to differentiate between testing and training data. I jump very easily between what I use color to mean. In this case, I meant something totally different than I meant in this case. In this case, the color represented the label of the training data, the outputs that I was trying to predict. In this case, I was using color to represent whether the points were in the training data or whether they were in the test data. Do you follow that? Okay, so I just want to clarify modes of communication. When I draw these pictures, there's lots of stuff to draw, but it's not like this is the problem we're really trying to solve. This is just some abstract representation of what I'm thinking. And really what it all comes down to is a model. Another way to think about a model is a box. And some number of things go in, and some number of things come out. And the number of values that go in could be 3 or 5 or 21 or 2 or 1. And the number of values that come out could be 3 or 5 or 2 or 29 or 1, whatever numbers I said. And the values that go in or come out could be continuous, or they could be binary, or they could be categorical, or whatevs. I don't think I've defined categorical yet, have I? What is a categorical value? Have I defined that? Okay, you know what a continuous value is, right? Continuous value can take any number from negative infinity to positive infinity. An example of a continuous value is 2.913748999999992. 1, 3. Okay. An example of a categorical value is banana. Did you get it? So orange, bananas, pears, grapes. Which one comes first? There's no implicit, so a categorical value has no implicit ordering. So categorical is no order, and it's kind of nominal or discrete. There's only a finite values. Continuous is ordered. There's some kind of spatial locality, and it's an infinite set. And there's something called discrete, which means you can't have a decimal point, but they are ordered. So ordered, is discrete values infinite or finite? You could actually do both, right? You could say, what are your possible ages? Well, between about 0 and 110, that's about it. Of course, if you're specific, age is actually continuous because you're not actually 14, you're 14.273, something like that. What's something that's actually discrete? How many kids do you have? That's pretty much discrete. Nobody has infinity kids, so, you know, just doesn't happen. Anyway, you can have discrete with a range or infinite set. These are different types of data, and you could feed any of them in and get any of them out, and you could train a model to support them. There are various types of models. Neural networks, which we've used before, are designed to work with continuous values. So a bunch of numbers go in. Remember the weights on sumo billiards? Numbers go in, a bunch of numbers come out. We use, I think, 2 numbers, one to point the direction and one to do the velocity. Decision trees, which we're going to work with today, are like this too. Any number of values go in. You can have any number of values go out. It's very common with decision trees to use categorical outputs. So it's, and you don't have to. You can do continuous outputs, but it's very common to use categorical outputs. And when you use categorical outputs, you usually only have one of them. You see why? There's not actually a great reason. It's just because that's usually the way it is. Usually if you're trying to predict a categorical value, you're trying to say something like, based on what we know of this person, is this person, that's dangerous, I don't want to label people. Based on what we know about this animal, is this animal a shrimp? As opposed to a crab or a lobster, right? You might want to use a machine learning algorithm to recognize shrimp under the ocean so you don't actually bring home a dolphin and then PETA gets mad and then you're in trouble. So, well, if you're trying to discern shrimp from dolphins, you're not usually also trying to ask, and are its eyes blue? Although you could. Okay, anyway. There are, by the way, I have a cold in case you didn't notice. I apologize in advance for blowing my nose a lot. If you want to come to my office hours or anything today, you're taking a little bit of a risk, just letting you know, so you can work. Okay. A decision tree is a type of model. Can you see why decision trees are really good with categorical outputs? Because this picture, right? I mean, if you're going to chop things up, there you go. How do you do continuous values with decision trees? For example, let's suppose you've got a 3.1 and a 2.8 and a 7.4 and an 8.3 and a 0.01 and a 0.02 and a 78. So now we've got 2 input dimensions, which I've represented on the horizontal and vertical axis, and 1 continuous output value. Can a decision tree handle this? Well, yes and no. It can't make a nice smooth function. Nevertheless, it can make a function. Let's chop this space up. Let's chop there, and then we'll chop this one. That's kind of worthless. Let's chop this one there. And I'll chop this one there, and I'll chop this one there, and I'll chop this one there. And now, if somebody says, okay, what value goes right here? I'd say 0.02. And if somebody says, well, what value goes right here? I'd say 2.8. And they say, what value goes here? I'd say 3.1. So with the decision tree, you can do continuous values. It's just that the space ends up being blocky rather than smooth. Is that good or bad?
Isn't that just like categorical, but you're just naming them with continuous value?
It is. In fact, I'm really chopping up the space just until I get 1 point in each place. And yeah, that is just like categorical values, but they're not categorical because they're continuous. Now, how good of predictions will this thing make? You can imagine that you have training data that looks like this, and your decision tree is going to basically make a model that looks like this. Pretend I hit that point precisely. And suppose your actual test data looks like this. We might at this point say, hey, it would have been better to use a neural net, right? Because then it would have been smooth, and then it probably would have made really continuous predictions. However, it's not going to be terrible, because all of these points are at least close, right? So to some extent, decision trees don't suck at what's called regression. That's predicting continuous values. They're just not really well designed for it. Okay? So intuitively, decision trees can make continuous or categorical predictions. They're used more with categorical, but you can do either. Okay? Reason that's significant is, wait a minute. Test labels. In the vowel data set, we're going to be predicting categorical values. Id, hide, hide, hod, id, hide, hide, hade, hood. Is that hood or hued? I don't know. You see that these are categorical values? Specifically, they come from this list, this set. This is the set of all categorical values supported in this label. Okay. In the soy test labels, we're also predicting categorical values from this set. And in the hepatitis test labels, we're also predicting categorical values. Oh. Somehow I thought we were doing regression. My mistake. Okay, so here's the deal. Never mind. Decision trees can do continuous values, but for this assignment, you won't need to do that. Okay. However, if we look at the features, the hepatitis training features, you will see there are age is real, so this is a continuous value, and male, female, this is a categorical. Albumin, that's a continuous value, right? Or protime. All these values are real or continuous, and all these values are categorical. So your decision tree needs to be able to handle both categorical and continuous inputs, and for this assignment, well, only categorical outputs. Okay? So you know what I'm talking about when I say that. Now let us move on to doing it. In all three cases, we're only going to have a single categorical output value. So you can, if you want to, assume in your implementation that there's only one output. And that's fine. However, there will be an arbitrary number of inputs. Okay. Well, that's about it. I think we've got the terminology down. Now let's start coding it up. Okay. Have I made it clear that, I think we've said this before, the random forest model consists of a whole bunch of decision trees, and they all vote. We've talked about that. You got that? Okay. There's such a thing called a decision tree. That's what I've been drawing here. Here and there. Imagine a whole bunch of these models, and some of them make their divisions in slightly different places. This spot right here, in some of the models might be blue, and in some of the models that might be red. And if they all vote, whichever one it is the most, that's the one that'll come out and make the prediction. This is called random forest because you have a whole bunch of decision trees, and they're all voting to make predictions, and it seems to work better than having a single decision tree. So that's what we're doing. We're going to be implementing decision trees and then making them all vote. Okay. Here is the code that I gave you. Let's start with main. Main looks like this. Inside static void main, it calls test learner, which is this function right here. And I'm testing a baseline learner. Let me look at that really quick. I wrote a simple learner for you here. This is a learning algorithm. It's a very stupid learning algorithm, but I provided it so you can see something working. Okay? The way this learner works is when you train it, it computes the average label. And when you use it to make predictions, it ignores your input values and always predicts the output, the average label. Okay? So in other words, let's go to this model. If this model were a baseline learner, then I train it, and when I train it, it computes the average of the labels. And when I make predictions, it doesn't matter what I feed in, it's always going to predict whatever the average of the training data labels were. So for example, if the training data looks like this, then the baseline model looks like this. And no matter what the input is, it always predicts that output value, right? Okay. So, the reason I provide this learning algorithm, baseline, is so that we can test something. So in main, I call test learner, and it tests it with the hepatitis data set, and then the vowel data set, and then the soybean data set. And let's look at what the test function does. First, it loads the training data. When I write code, I like to put my code in blocks, and I make a comment at the head of each block that says what the block does. So whenever there's a space, that's where a new block starts. So you can just read this comment, load the training data, and now you know what all this does. Okay. Then I train the model, so I call learner.train, and I pass in my training features and labels. And now the baseline learner learns what the average label is, and it ignores my training features. Then I load my test data, which is pretty clear, and then I measure accuracy, and I report it. So let's run this and see what it does. There you go. So, at the hepatitis data set, my baseline learner misclassified 14 out of 78 test patterns. In other words, 14 people were told they were going to die, and they're not. They're going to be mad. Or else 14 people were told they're going to live, and then they died. One of those two. What's that?
In which case, oh well.
In which case, oh well, right. Yeah, exactly. Who cares at that point? I mean, surely they had nothing important they needed to do before they died. Okay. With the vowel data set, I misclassified 417 out of 495. In other words, the most common thing they said in that microphone isn't very predictive of what they're about to say in the microphone. Whereas, when it comes to hepatitis, if you just look at the average whether you live or die, most of the time that's going to make a good prediction. Does that make sense? Do you see how these are totally different magnitudes of problems? What people usually say in a microphone isn't what they're going to say in the microphone next. So this problem you could say is much harder. Whereas predicting whether hepatitis will kill someone, pretty much trivial. They're all going to die. Or live, one of the two. Should we find out which it is? I want to know. Okay, hepatitis test. It's like most people live. Therefore, if you get hepatitis, you're probably going to live. Okay. So don't even worry about it, all right? Okay. Bad advice. And the last one was the soybean data set. Misclassifies most of them, so I guess it's a harder problem, something like that. Okay. So when you implement your decision tree, you're pretty much going to take this baseline learner and copy it, and then change it to become a decision tree. When it does, you can expect better predictive accuracy than that. If you get worse predictive accuracy than that, there's something wrong with your decision tree, because baseline is a really stupid learner. And decision trees are kind of smart learners, so it should get better. Okay, so after you code up your decision tree, what you're going to want to do is add a line right here that does test learner new decision tree, and see how well your decision tree does. And then after your decision tree works, then we'll have you implement random forest, which in this case contains 50 decision trees. And that one should even beat decision tree. It should do even better. And so this is what you'll turn in, is code that will report accuracy for baseline and decision tree and random forest. And so it'll print 9 total predictive accuracy measurements. This is how many it got right, and this is how many it did. And because we're all training and testing on the same split of data, this will pretty much tell us who did it right and who made bugs, because everyone that did it right will get nearly the same accuracy, and if you did it totally wrong, you'll get totally bad accuracy. Okay? And that's that. All right. So now let's start coding this thing up. I'm going to comment out this so that it will compile again. And let's look at the baseline class. So my baseline learner extends something called supervised learner. We better look at that and see what it does. My supervised learner class has 3 abstract methods. You all know what abstract methods are, right? When you extend a class with abstract methods, you have to implement these methods, or else the compiler will yell at you. That's it. So the name function, that's easy. You just return the name of your function. The whole purpose of that is so when you test it, it can print out the name of what it's testing. That's easy. Train method, this is the hard one. This is where you build your decision tree. Predict, this is where you use your decision tree. And count misclassifications, this is a useful function that I wrote that you can use. Basically, it's used right here to measure how bad your learning algorithm is. That's kind of a negative way to put it, isn't it?
How good your learning algorithm is?
No, it measures how bad. If you want to know how good it is, you can subtract from 100% and see what the goodness of your learning algorithm is, but I measure badness because I'm a pessimist. Yeah. The number of correctly classified ones is the total number of training data, test samples minus the misclassifications. That's pretty obvious, right? Okay. So ultimately what it comes down to is you're going to write a new train method, that's the hard part, and a new predict method, that's not so bad. And then you will have made a decision tree. Then you'll make an ensemble of them, which is even cooler and be even more powerful, and then you're done. Okay, let's do that. Let's make sure I still build. Oh, there's more code I didn't show you. There's a matrix class and a vec class. Here's my vec class. It represents a vector. But in this case, vector means a list of continuous, double precision floating point numbers, not to be confused with an array list or a dynamic vector, which is often used in programming languages. That's why I called it vec instead of vector, so we wouldn't get confused. This class actually just has a bunch of static methods that operate on vectors, such as print, set them all to some value. So it just loops over the vector and sets them all to the value you want. Computes the squared magnitude of a vector, sum of the squares of all the elements, normalizes it, copies a vector, adds 2 vectors together, dot product. Basically a bunch of vector operations. Why? Because it's useful. You might need it. If you need vector operations, there you go. There is also a matrix class. What is a matrix? It's like a square vector of numbers. It has rows, it has columns. Think database table. Inside of a matrix, you have a whole bunch of numbers. Where are we going to use a matrix in this assignment? Yeah, see, we got this data. And this is basically a matrix. Once it's loaded into memory, female will have the value of 1, and male will have the value of 0. I meant no bias in that ordering, but they had to come in some order, and the first one gets 0, and the second one gets 1. If there were 6 of them, they would be 0 through 5. Okay, so by the time it's loaded into a matrix, all of these values will be converted to numerical form, but the categorical ones will have discrete values from 0 to n minus 1, where n is the number of categorical values, and the continuous ones will just stay what they are. And now it'll all be loaded into a matrix. So you can see here in this train method, I pass you a matrix of features and a matrix of labels. In both cases, the number of rows will be the same. Do you see why? Because we're mapping, if you have these features, you should have these labels. This is the training data. These are examples of, if you see this, you should predict that. Okay? So they better have the same number of rows. If they don't, throw an exception. That means something bad happened. They don't have the same number of columns, though. You can map from 10 inputs to 1 output if you want. And in fact, the label matrix will always have 1 column because we're only predicting 1 label. Although presumably you could have an arbitrary number of columns. So if I were writing this assignment, I would handle an arbitrary number of labels just because that's cooler. But you can do it either way just as easily. Okay? So here we're using matrices. And here we're using vectors because when you make a prediction, we only predict 1 at a time. So here I'll pass you some number of values from my test data, and you're supposed to return a prediction that goes with that input. Okay, is the assignment clear, what you're doing? All right, now let's do it. Java, still built. Copy baseline learn.java to decision tree.java. Okay, decision tree.java. This is now my decision tree class. And I've already written the name function for you. Bam. Okay. Now we're going to write a decision tree. The whole purpose of train is to build the decision tree. The purpose of predict is to use the decision tree. All trees have a root. Actually, before we do that, I provided a little bit of useful stuff here. Let's go paste that in. I made these classes called nodes. Do you know what a node is? A node is one of those circles that's connected by lines when you draw a tree. And there's stuff in the circle, and that's what a node is. Okay. So, node, I will make one called root. Because every tree has to have a root, and the model somewhere needs to have a root to this tree. So the whole purpose of train is to make the root, right? Best way to build a tree is recursively. I'm going to say root equals build tree features, comma labels. And now I'll write a recursive function that returns a node named build tree. It takes features and labels. Okay. Now, inside here, I need to start chopping up this data until it gets small. And once it's small, then we've got a leaf node. How about let's start with the base case. You remember the whole induction, recursion, base case stuff? Studied that, right, at some point? Okay. Let's start by saying if features.rows is not equal to labels.rows, row new equal argument exception. Wow. Okay. Now I'll say if features.rows is less than min size, else I'm going to add a new value here called min size, and by default, how about we have it be 1? And we might add a setter if we want to set min size to something else. But essentially what I'm saying here is I'm going to keep chopping up this data. I'm going to cut and cut and cut until I'm down to min size number of total values. And once I'm there, now I'm going to build a leaf node. Let me see how I make a leaf node. Well, we have a constructor. Let's see what I have to work with. In my baseline class, that's going to be really useful information. I'm going to basically steal this code right out of my baseline train method. Because remember what I said the baseline learner does? It predicts the average label from whatever data you've got in your features. Well, suppose I've chopped my data up until I've got some very small number of values left. Which one of those should I use for the predicted label? You see that the average pretty much is a good prediction? So I'm going to take this code right out of here, and I'm going to use it to implement my constructor of my leaf node. Leaf node. Let's see. Gotta pass in a matrix of labels here. And instead of mode, I'm going to rename this to be label. There. So now, my leaf node, I pass in a matrix of whatever labels I've got left after chopping it up, and this label now becomes the average of whatever's left in that data. So down here, I can say, in my build tree, if I run out of data, I can say return new leaf node of labels. And I have now written my base case. When I run low on data, find the average of what's left, that's the prediction for that region. And now I've done half of it, now I just got to do the recursive half, and then I'm done with the build tree method. Right? Okay, so how are we gonna chop stuff up? How would you do it? We've got a matrix of features. What does it even mean? I mean, we've got this picture right here. If I can find it somewhere. We've got a picture here of some data, and I've drawn lines to cut it. What does that mean in terms of, now we've got a matrix of features. Wait, here I am. A matrix of features, and I want to cut it. How does one cut?
This is a generator. It does leaf node inherit from just node.
Leaf, I believe it does. Let me see. Leaf node extends node. The answer is yes.
So I would create a node that just arbitrarily picks half of the matrix.
Yeah.
Called the tree again.
Okay. Essentially what we need is we need to chop the matrix. We need to chop the data somehow. Do you see how these lines that chop it are one of the input dimensions? They're both one of the dimensions and some value in that dimension. Well, that's what we need. So we need to pick a dimension. I'm going to say int dim
Sorry, so
equals.
you could take one of the features, pick an arbitrary point, and then say every one of your, like if it's a continuous map, everyone less than that, you're gonna go to this arbitrary, you're gonna use basing
Yep.
it off of various features.
Yeah, so essentially at this point, I'm going to pick a random dimension. In this case, there's only two dimensions, so it's either 0 or 1, horizontal or vertical. Let's suppose I pick vertical. Well now, on the vertical dimension, I need to pick a value. Let's suppose I pick right there. It's value. Ironically, picking the vertical dimension makes a horizontal line. And I'll say everything in that dimension that has a value greater than or less than this goes on this side or that side of the line. And so basically I have now cut my data in two, right? Okay, so I'm going to say my dimension, I'm going to need a random number generator. So let's come up to the top. Import java.util.random. Star. Import star.star. This totally should work. Okay. Random R. Rand. Rand equals new random. I hate when random number generators are random. I like seeding them. You don't have to agree with me on this, but let me tell you why I always seed my random number generators. When I code, I make mistakes. I'm sure you never do. But when I hunt down those mistakes, I really hate when I've been digging through the debugger for 3 hours and I finally find something and I just need to run it again to nail down where the bug is, and it behaves differently. Doesn't that just drive you nuts? If you seed your dumb random number generators, your program will behave the same every single time.
Shouldn't you just initialize an array of values then instead using a random number generator?
No, because that would waste a lot of memory. And I would have a lot of hard time determining that they were really chaotic.
Well, I was just saying it would defeat the point of using a random number generator.
It would, you're right.
Well, I mean, once you've done your testing and found and figured out everything working, then you can change it to it's truly random.
That's fine, but you know, you're still running the risk of, it worked on my machine, and then the grader says it doesn't work, and then you've got, but maybe it's because of the random seed, please try it again. I ran it twice and it didn't work. Try a third time. You know, I mean, just seed your dumb random number generator. I don't know why that's become such a peeve with me. For some reason, I can't seem to persuade my Paradigm students to seed their random number generators. They keep saying, but then it's not random. That's the point. I don't want random numbers. I just want chaotic numbers. Okay. Where am I? Is rand.nextInt features.calls. Right? The number of columns is the number of dimensions, because here's an example of some data. However many columns there are, that's how many I'm going to choose from. Right? These are the dimensions. Do you agree with me? If you don't, you're wrong. Where's my code? Getting back here. Okay, now we need a value. Where are we going to get a value that's plausible? Val. Excuse me. Okay, well, we've got these features right here, and they contain all the plausible values. I say we just pick one of them. Let's take features dot row of and dot next in. Let's just get a row here. So double row equals features dot row ran next in features dot rows. What I have just done right here is I have drawn a random row from my features matrix. With me? Double val equals row of dim. I picked a value in the dimension of interest from a random row in my features matrix. Essentially what I have done is, not you, let's keep this one. So I've picked a dimension already. I've picked this vertical dimension. Now I'm going to pick one of these points at random. Let's suppose I pick that one. That means that's the value I'm going to use, so my line is going to go right there. Do you see why that's always I mean, it's not necessarily great, but it's not going to be a stupid way to divide your data, because if you pick all your points at random, it's not very likely you're going to get one of the extrema. Chances are you're probably going to get one in the middle, and it's probably going to cut up the data. And you'll never pick a value that's just way out in the boonies, right? Here's a value that does absolutely no good. So I have picked a dimension, I have picked a value, and now I need to divide my data. In order to do that, you're probably going to have to go look at my matrix class and figure out how to chop a matrix in half. A lot of people will panic when they see that there isn't a simple method here called chop in half. However, it's not that complex. Just allocate a new matrix, write 2 for loops, copy from one into the other. You see that that's not that bad? Let's figure it out together though, just so I don't make you waste a lot of time studying my code. But a matrix really is just a two-dimensional array of stuff. So, well, what do I need to do here? A matrix can print, I can save to R formats, I can set the size, that's kind of useful. Copy metadata. Here's a slight concept. If you make a new matrix, it's going to assume that the matrix is full of all continuous values. And we're going to actually have to handle that differently. If dim refers to a continuous dimension, then we need to do a greater than or less than thing, as shown in this picture. What if this dimension, however, is a categorical dimension? For example, this dimension is your hair color, and your choices are red, blonde, brown, and black, because all hair is one of those 4 colors. Then what do? Is black greater than or less than blonde? We don't know.
I would say greater since it's darker.
Okay. I could get furious and say lighter is greater, but you know what? Don't even care.
I mean, some form of ordering.
Okay. With continuous values, we're going to do greater than or less than. If we're doing categorical values, we're going to do whether it's equal to or not equal to. Does that make sense? So I need to ask the question, if this thing is continuous. Now my matrix provides a way to do that somewhere, and I need to point this out to you as soon as I find it. Aha, value count. Returns the number of values associated with the specified attribute, or column. Column, attribute, same concept here. 0 equals continuous. 2 is binary, 3 is trinary, etc. So all I need to do here is say if features dot value count of dim is 0. Else, okay. So if it's continuous, then I'm going to say all points less than val go in other matrix. And if it's categorical, all points equal to val go in other matrix. And all points not equal to val stay in this matrix. And so now we've got 2 matrices. And once I split my matrices into 2 parts, what am I going to do? I'm going to simply recurse. I'm going to say, well, okay, I'm going to say interior node. Interior node. Node.a equals, is it A? Let's see what I'm working with here. A and B apparently are the 2 dividers. So I'm going to say A equals build tree of this features, this labels, and node.b equals build tree of that features and that labels. Where this features and this labels and that features and that labels are 2 matrices, which I have chopped my matrices into. You follow that? So whereas here I have 2 matrices, features and labels, Now I have 4 matrices. The features on one side of the line, the labels on that side of the line, the features on the other side of the line, and the labels on that side of the line. So I've chopped up my data, and I'll return my node. And so now this whole thing will build a tree. It'll build up the interior nodes by chopping the data up until they reach a small number of points. Once I do, it'll compute the baseline prediction, meaning the average labels at that point. And I have now built my entire decision tree. There you go. I've written my build tree function. Okay. I just did all the hard stuff for you. Except you're still going to have to write code to split the matrix. And that's a little bit of a pain. At least I'm leaving something for you. I hope I haven't done so much that you won't think about it. Please make sure you understand what you're writing and what you're doing. That's the whole point of these exercises. I don't care if you can complete the assignment. I care if you get decision trees and
Can you
ensemble.
go back to that build tree function?
Yes.
So in the with features dot value count down below,
Yeah.
both of them say go in other matrix.
Yeah.
Is that supposed to say that? Or?
I'm not sure I wrote this very well. By the way, this won't compile, in case you're
Yeah.
trying to compile that. My point is, right here, we're going to have a for loop. It says for int I equals 0, I is less than features.rows, I plus plus. And we know that labels.rows is the same as features.rows, right? You have to have the same number of features and labels. And we're going to, for each one, we're going to say, in the dim dimension, is your value less than val? If so, go over there. Otherwise, go over there. Right? Go this way or go that way. And so, split the data is what we're really doing here. Likewise, in the categorical case, we will split the data. Except in this case, we're going to check in the dimension in the dim dimension, is your value equal to the val that I picked? If so, go left. Otherwise, go right. And when I'm done, I'll have taken my matrices and chopped them into 2 matrices. All I'm doing is drawing a line. I'm chopping this region that used to be 1 matrix into 2 matrices. And now this new matrix contains 2 values. Whoops. And this matrix contains 1, 2, 3, 4, 5 values. Whereas there used to be 7 values. So I used to have a 7 by 2 matrix. Now I have a 2 by 2 matrix and a 5 by 2 matrix. And if I were to lay them on top of each other, I'd have my original matrix. Except the rows might be in different orders. Is it sufficiently clear that taking each row in your matrix and moving it to another matrix, one way or the other, is the same thing as drawing this cutting line, is the same thing as doing the decision tree division thing, is the right thing to do? Okay.
I have a question.
Yes, please.
We would have to do this for both the features and labels, correct? If we split a given row out
Yes.
from the label or the features. we
If the
have to-
features go this way, the labels go with them. The features and labels never get parted from one another.
Okay, so follow up then.
Yeah, you might even, some people like to put them in the same matrix. I keep them in separate matrices because, well, I do.
So if the first thing we do in that function is join them into 1 matrix, is that fine?
Fine with me, yeah. If it works, you're good. The reason you want to end up splitting them is when you make the leaf node, you will only use the labels and not the features. Because you don't care what the features are at the leaf. By the time you reach the leaf, you want to know what the label is. Can you see why? You don't color all of this region with some X value, you color it red, because red is the name, the color of the labels. Okay, so when you're dividing, you divide on features. When you reach a leaf, you have labels. Interior nodes split on features, leaf nodes specify a label. That's how decision trees work. Okay. Now, let's talk about how to do a predict. How am I going to write the predict method? How would you do it?
It's 310.
It's 310. Oh, thank you. Well, you could do it recursively or iteratively. I'm just going to give you the quick summary and then we'll pass back the test. Thank you. You start at the root and you check, does the dimension we split on in this vector go this way or that way? And you just run down the tree. Then you go to the next node and you see which way you go. Then you go to the next node, you see which way you go. And when you finally hit a leaf node, whatever output vector is there, you copy it into out. You get how to predict? You just use the tree. Questions? Okay. I think you know enough. You can code up a decision tree now. I believe that's the case. And we haven't quite gone over bagging. We'll have to do that next time. But bagging's really easy, so I think you're all set. Let's pass back tests.